Okay, so last time we started looking at electronic structure of atoms and what the valence shell is, and we talked about how we can figure that out just by looking at the periodic table. You don't necessarily have to count up the electrons in all these buckets. And then I kind of told you that it was important and it had something to do with what the atoms do, but I didn't really say more than that because we ran out of time. So today we're going to look at the consequences of that. Before we do that, the other thing we should look at that I know you did a little practice on in your homework is how we classify matter. So we're going to classify matter into 4 overall categories, but first we're going to split it into 2 categories and talk about the difference between those. And now that we've done some lab, I think maybe it'll make a little bit of sense also. We start with just matter, which is anything made out of atoms, anything with mass. And then we can classify that into 2 categories. Anybody know what are the 2 categories that we can put something in? One is pure substances. And the other one? If something's not a pure substance, what is it? You know? Okay. It's a mixture. So you've either got a pure substance or you've got a mixture. All right, what is the difference between a pure substance and a mixture? So there's no naturally found mixtures? No? Yeah. All right.
Pure substance is just one thing. Shares 2 things.
Or more things. Yeah, okay, so what do you mean by a thing? The thing.
Substance.
But that's in the word, right? It's a hard thing to, I mean, it's hard to define this. Elements could be a part. So elements are definitely pure, right? They're one kind of thing. But is every pure substance an element? Okay, getting there. So think about something like water. Is water a pure substance? If you just have water. People like yes. What? Did you say cat water?
Tap.
Or tap water. No, like pure, like only water. 100% just H2O molecules. Is that a pure substance or is that a mixture? It's a pure substance.
Yes.
But it's made out of more than one element, right?
It's a mixture.
But it's a mixture?
Yes.
Okay, so these things get a little tricky. So let's break it down into the next categories and then we'll try to make a little bit more sense out of it. So mixed pure substances can be broken down into 2 categories. And the 2 categories are elements and compounds. So water actually does fit in this category because it's a compound. Elements are only one type of atom, and compounds are more than one type of atom, but the key is that they are chemically bound together. So elements only consist of one type of atom, and compounds would be 2 or more types of atoms. And then here's the key, that they are chemically bound. So the essential difference between pure substances and mixtures and is that pure substances can only be broken down by chemical reactions, whereas mixtures can be separated physically. So what does it mean to separate something chemically versus physically? What happens when you separate something chemically that doesn't happen when you separate it physically? Yes. What does that mean? What? It's always a fire?
Like there's a reaction.
Yeah, so that's some evidence of chemical reaction. So you're breaking something down, you're actually changing what it is. You're destroying it and making something else. So think again about our example of water. Water is made of hydrogen and oxygen atoms, so it's a compound. And you can break it down into pure hydrogen and pure oxygen. What is pure hydrogen like? What are some properties or characteristics of pure hydrogen? It's a gas. Invisible. Invisible gas. Anything else you know about it? It's really flammable, explosive. So is that the same as water? Definitely not, right? Same thing with oxygen. Oxygen gas is, or oxygen is gas. It's invisible, colorless. You need it to breathe and make your body work. So it's not the same as water. So you really change at an essential level the identity of what the thing is when you break apart a compound into its constituent elements.
So in this case, hydrogen would be the element, water would be the compound.
Right. Right. So let's take pure hydrogen then. So you take pure hydrogen, you can't break that down any further. It's just hydrogen atoms. So that's an element that can't be broken down any further. Compounds can be broken down, but only chemically, which means you're actually breaking apart chemical bonds and changing what that thing essentially is. Mixtures, on the other hand, can be separated physically. So not just chemically, but physically. What's the difference between separating something physically versus chemically?
You need to go in there and
Yep.
make sure it's just like a bunch of solid stuff. Or just mixing, or it could be liquid.
It could be whatever, but right. So when you separate something physically, when you separate a mixture, you're not changing what the identity of any of the components. So let's say you have salt water. We had in lab on Tuesday. Salt water is a mixture of water and salt, sodium chloride. So two compounds together. How do you separate the two compounds in salt water? Yeah, you can evaporate the water and it would leave the solid sodium chloride behind. You can condense that water and actually have it as pure water also. So you separate those things, you still have salt, you still have water. You haven't changed the chemical identity of either of those things. You've just separated them from each other. So that's a physical separation. When you don't actually change the identity of anything, you simply separate them. So there are two types of mixtures as well. Homogeneous, heterogeneous. What's the difference between those two types of mixtures? What do you mean by the same? It dissolves. So that's one way of thinking about it. Homogeneous mixtures are sometimes known as solutions because the composition is uniform throughout. A homogeneous mixture doesn't have to be a solution, but it often is. So you think about something like, again, salt water. If you have a container of salt water and it's properly mixed and everything, you don't see salt on one spot and water in a different spot. It's all intimately connected, actually down, in that case, down to the molecular level, where you have individual sodium and chloride ions and water molecules kind of all together. So that's an example of a homogeneous mixture. It's the same throughout. You can't see like the different parts of it. So what would be an example of a heterogeneous mixture? Like trail mix, sure. Yeah.
Just throwing a bunch of things and you identify all the-
Yes, definitely. So when you can identify all the different parts, you have a heterogeneous mixture. Not uniform throughout, has clear separate domains. If we stick with our water example, if instead of salt water we made, let's say, sand water, don't drink sand water, but if you put a bunch of sand in water, it would not make a homogeneous mixture. Or you can always see the sand and you can see the water. They don't dissolve. That would be an example there. All right, let's look at a few examples and see where we would put some stuff here. What about one of our reactants from the lab on Tuesday? Sodium bicarbonate. Where would you categorize that? First, let's do it in steps. So would you call that a pure substance or a mixture? Pure? Why pure? Yeah, so it's one type of thing, right? It can't be physically separated. Even though it's got two words, sodium and bicarbonate, we know that it's got a chemical formula, NaHCO3, and if we were to separate it anymore, we'd be making something different, like we did in lab. We separated the CO2, which became a gas. And that was something different. So when you break this down, it becomes something different. That makes it a pure substance. Because it's a pure substance that's made out of different elements, that makes it a compound. All right. Try another one. Coffee. Is coffee a pure substance or a mixture? How do you know it's a mixture? Yeah, so you know it has at least a couple things. It has water and some other stuff. Flavor molecules, caffeine molecules, some sugar, some other kinds of stuff, colored molecules, all kinds of stuff mixed in there that makes coffee. So it's definitely not just one pure substance. And would you call it a homogeneous mixture or a heterogeneous mixture? Probably homogeneous, right? You don't see the different parts in it. Kind of depends how you take your coffee, I guess. If you like your coffee with sand in it, it would probably be heterogeneous. I prefer not sand coffee, so it would be homogeneous. Even if you put a bunch of other stuff in there like sugar or milk or syrup, or that would still be homogeneous. It would all be mixed. All right. So that one's pretty clearly a homogeneous mixture. Okay. What about blood? Homogeneous? It's a mixture. Yep, because there's a lot of different stuff in blood. And you're saying homogeneous? Anybody say heterogeneous? Heterogeneous? Why? There's different blood cells. A lot of different parts in it. Yeah, so this one's kind of a trick question because it depends on how you're looking at the blood. And so this question of whether something is a heterogeneous or a homogeneous mixture is not necessarily one that can obviously be answered one way or the other every single time. So if you just had like a big jar of blood, sorry, I forgot to bring my big jar of blood, but if we had a big jar of blood on the table, we'd probably categorize it as homogeneous because you can't see the different parts of it, right? If we added some sort of anticoagulant or something. If we let it coagulate, if you've ever seen blood eventually sort of clumps up and you can spin it down in a centrifuge, you can separate the cells out, and that definitely looks very heterogeneous. Same thing if you looked under a microscope and you could actually see the different cells. You still wouldn't see the molecules dissolved in the blood, like all the sugars and whatever else, But you could see the cells in the different parts, so that would look pretty heterogeneous too. So a lot of it depends on your own experience and how you're picturing that. So if I gave you an exam and said, categorize blood, and it was a multiple choice question, and I marked it right for one of those and wrong for one of those, that would be pretty mean and bad. Like, because I can't do that. That's not fair. Because there's different ways you could interpret that. All right, can somebody give me an example of another compound? What?
Sodium chloride.
Sodium chloride, sure. Yeah, salt, sodium chloride. On its own would be a compound, NaCl. If we dissolved it in some liquid like water, that's now a mixture. What are some other ways that we can separate mixtures besides evaporation? That's evaporation. Burning is really a chemical thing. So when you burn something, you're kind of breaking it down chemically. There's a few different ways, a few different methods that you can use for physical separation. What do you think of? Yeah. Okay, so sometimes you can, let's say, that's a really good example, like air. Air is a mixture, right? What's in air? What are some of the things? Oxygen, nitrogen, carbon dioxide. Yeah, there's water vapor in air, quite a bit of water vapor in air. There's other trace gases like argon and helium and stuff like that. So if you want to separate those things from each other, like you can get a tank of pure oxygen, right? So you could separate the air and get the oxygen. One way to do that is to cool it down. And the different gases in air, and this is one of the ways that air was first identified a long time ago, what was in it, you can actually condense the different gases at different temperatures. So I don't know what the boiling points are offhand, but the water would condense out first, and then probably the carbon dioxide, and then the nitrogen, and then the hydrogen. I'm not sure that's exactly right, or the oxygen's in there somewhere. You could condense them out at different super low temperatures and collect the liquid or solid versions of those to separate that. So that's one way to do it. There's other just like more basic means of doing it. Like you could literally just take some tweezers and pick things out of a mixture if the pieces are big enough. That's a physical separation. You could filter things. That's a really important means of physical separation that we do in the lab. If you have a solid and a liquid that's a mixture together, but they're not dissolved, then you just pour it through a filter and the solid stays on top and the liquid goes through and you've separated that mixture. So that's another physical means of separation since you're not changing what that is. All right, so do you feel okay with that? Categorizing those things? Okay, good. So let's go back down to our small view of matter and look back at the electrons. So Tuesday, we talked about protons and neutrons. We talked about finding the overall number of electrons from balancing with the protons. And then we talked about these buckets and these valence electrons. So we're going to put that together now and start looking at ions. Ions are charged atoms which means that instead of being neutral, they have an overall positive or negative charge. And depending on that charge, we have a name for them. Positively charged ions are called cations, and negatively charged ones are called anions. And what do you think causes that charge? Yeah, but what causes that? What's going on inside the atom that makes it positive or negative, positively or negatively charged?
There's magnetic force.
Quite. So let's say you have a sodium atom, and then you have a positively charged sodium cation. What's the difference in those two particles? Yeah, so it has to do with the balance of electrons and protons in the atom. In a neutral atom, the electrons and the protons are always balanced out because you always have as many electrons as you have protons, and so you have the positive and the negative cancel each other out, and you have a zero, you have neutral. In an ion, that's not the case. You have different numbers of protons and electrons. So let's take a look at the difference. So here's a sodium atom. And here's a sodium cation with a +1 positive charge. So in the regular neutral sodium atom, what's the charge, or how many protons and electrons do we have? Look over at the periodic table. Did you find it? 11, right. So the atomic number tells us we have 11 protons. And then because it's neutral, we must also have 11 electrons. So then if we want a sodium cation, do we add a proton to make it one more positive? What do you think? There's two ways we can make it positive, right? We can either add a proton or we can get rid of an electron. Which one is the right one? Why? Just guess. Okay. Anybody have a why? What happens if you change the atomic number? Yeah, exactly. You change what it is. So if we add a proton to sodium, we actually make it into magnesium, because if any particle with 12 protons is going to be called magnesium. So if we want to keep that sodium identity, we have to only mess with the charge by changing the numbers of electrons. So sodium will always have 11 protons, but if we want it to be positive, we get rid of one of the electrons so that now it has one more proton than electrons. If we go the other direction, like let's look at chlorine and chloride, the 1- anion, the -1 anion. Same thing for the neutral chlorine. We're going to have an equal number of protons and electrons. But now for the charged particle, for the anion, we still keep that same number of protons and we add 1 electron. Yeah. Right, because if you change the number of protons, you'll always change what the element is. And nuclear reactions are the only case where where something changes the number of protons. Chemical reactions are always just messing with electrons. All right. So that's basically how you do it. You can also make ions that are more than just one change. So for instance, oxygen tends to make a -2 ion. So plain old neutral ion, oxygen would be 8 protons and 8 electrons. And oxygen 2-, which is called oxide, would be 8 protons and 10 electrons. Right. Take them away. Yep, exactly. So how you write that, you may see it done a couple different ways. I think the most standard way is like this, where you put the number in front of the charge, and then there is no number when it's just +1 or -1. You may also see it the opposite, where it says -2 instead of 2-. And then there's a third way where you just make like 2- signs. you may see that also, but this is probably the most common way to do it. It's the clearest. It makes the least amount of potential conflict with whatever is next to it. All right, so notice that sodium ion has 10 electrons. Oxygen ion also has 10 electrons. The most common ion of fluorine, which is the next one over in the row, also has 10 electrons. So what do you think special about 10 electrons?
Noble gas.
Okay, go ahead.
It makes them stable because then they have 8 shell, because they already have 2 in their.
Yeah, so we can explain this by going back to the buckets. Thank you. If we think about the different shells, remember that the first one holds 2, the second one holds 8, and the third one holds 8 for our purposes. And so as it turns out, there's a special stability for atoms when their shells are either full or empty, totally full or totally empty. So we can say that these are more stable when the shells are totally full or totally empty. So there's only a few electron counts where that's the case. And this, by the way, is called the octet rule. Because most of the shells, there's something special about 8. That's where that octet rule comes from, even though the first one only has 2. But there's only certain counts of electrons. So if an ion has 0 electrons, that would fit. If an ion has 2, that would fit. If it has 10, that would fit. And if it has 18, that would fit. That's pretty much it. So there's special stabilities when that can happen. And the really powerful thing about this concept is it allows us to predict what types of ions things will form. So I just told you up here a bunch of ions that are really common, like that sodium makes a +1, and oxygen makes a -2, and fluorine makes a -1. But there's no need to memorize all that stuff. We can figure that out just by thinking about the shell numbers. So it works like this. If we take oxygen, oxygen's got 8 electrons, right? We put those 8 electrons in the shells, 1, 2, 3, 4, 5, 6, 7, 8. We can see pretty clearly that if it got 2 more electrons, it would have all full and empty shells, right? See that? So that tells us that oxygen is really going to want 2 more electrons to become stable. And that's exactly what we see. And this is true in reality. So oxygen, atomic oxygen, O2, oxygen gas, is highly reactive. It reacts with all kinds of stuff. That's what we call oxidation in a lot of cases. It can help things burn. Combustion is that reaction with oxygen. Oxide ion, O2 minus, is extremely stable. It's an important part of most rocks and minerals. So it's something that pretty much just stays as it is. And part of that is because of that extraordinary stability from the full shells. In sodium's case, we start with 11 electrons. So that's like this. And in this case, it's easier for sodium to lose that 1 electron to get the full and empty buckets than for it to gain 7 more, which would also fill the buckets. So whatever amounts to fewer electrons moving around is usually what ends up working. So sodium would lose that electron, become sodium +1, and then that fulfills that octet rule. Yeah.
Does that mean that sodium plus 1 is more stable than sodium?
Yes, and that's true as well. That you can, regular sodium, so like neutral sodium, is a metal. It's a really soft metal. You can kind of cut it with like a butter knife, and it's super reactive. If it touches water, it forms hydrogen gas, and if a bunch of it touches a bunch of water, it actually explodes, and it causes a really dangerous kind of fire because it also reacts with the stuff that fire extinguishers have in them. So you need a special, if you're working with plain sodium metal, actually any of the metals over on that side of the periodic table, you need special fire extinguisher called a class D fire extinguisher to put those out. So that's sodium. Once sodium loses its electron and becomes sodium plus 1, now it's like salt. It's regular old sodium ions, which you need in your body, which are not reactive anymore, and so on. It's actually hard to get sodium. It takes a lot of energy to make sodium metal because the sodium ions are so stable. So yeah, big difference. All right, let's predict some of these ions then. If we took nitrogen and I asked you what charge would you predict the nitrogen ion to have, what would you predict? Why? So think about the number of electrons. Think about if you would add or subtract electrons and what that would make. Add 3, why?
7 to 2. So you had 5 closer to it.
Yeah, so we can, if you remember from Tuesday, we can look at the periodic table and we can see that nitrogen is in group 5A, which tells us what? What does that 5 tell us? There's 5 electrons in its valence shell. So if there's 5 electrons in its valence shell and it wants that shell to either be full or empty, it can either lose those 5 electrons or gain 3. 3 is less than 5, so it's more likely it's going to gain 3. And that makes it a 3- anion. So we would expect the ion of nitrogen to be N3-, which it is. That good? That's it. That's all there is to it. So even weird stuff down on the periodic table. Look at tellurium, number 52. If you were going to guess what kind of an ion tellurium forms, what would you guess?
Negative.
2 negative, why? Yeah, so same idea, 6 valence electrons, so it's going to gain 2 and become -2. Now, because it's lower in the periodic table, it does a bunch of other weird stuff too, but it also forms 2- anions as we would expect. So we can generalize about whole groups on the periodic table just by their position and their number of valence electrons. So if we do make a quick picture of the periodic table here. Let's just give ourselves some groups here. Okay. So something like that. So we've already done this. We can generalize. Wait, I think I missed a group. Yeah, I missed a group. Sorry. Make smaller lines. Okay. We can make some generalizations. So we can say everything in this group 6A here is going to generally make a -2 ion. That's what we just generalized, right? And everything in 7A is going to make a -1. And everything in 5A is going to make a -3, which actually ends up not being quite true because of that stair thing. But anyway. And then what about the next one over? What about 4A? That would kind of go either way, right? Because if you've got 4 valence electrons, you could lose those 4 or you could gain 4. And in fact, those don't really make ions, anti-ions in the traditional sense. They kind of do other stuff because it ends up being hard to lose or gain that many electrons. So we don't really have a good general ion for that. What about 3A? What do you think is going to happen there? Positive 3, right. It's going to lose those 3 valence electrons rather than gaining 5. And that's not true for all the members of the class, but because some of them are metals and other stuff's going on. But aluminum for sure, which is a really common metal, is definitely going to have a +3 charge. And then the only other 2 places where we can generalize this are way over on the left, 1A and 2A, like we did with sodium, are always going to have +1 and +2 charges. All right, questions about that? Okay, then let's talk about building ionic compounds. Oh, no, don't do that. Ionic compounds are when we have more than one ion together. And in fact, that's how ions always exist. You can't really have 3 ions that are positive or negative. You can't get a jar of sodium ions. They always have to have the opposite charge with them. So when we talk about ions, we often talk about them in compounds, which would be the cation and the anion together. So ionic compounds are a cation and an anion. And our job then, what we're going to work on now, is putting them together in such a way that the overall compound is neutral. So for example, let's say we wanted to know how to write a formula for the compound sodium chloride. We can do this. The first thing you do is just write down the symbols for the ions that are given. Sodium is easy enough, is Na. Anions often change their name a little bit, and we'll learn more about that in the next chapter. But chloride is going to be coming from chlorine. You can probably figure that out at least. So you would look it up on your periodic table, and you'd see a Cl. As we're doing this today, if you have a periodic table handy, you can grab one that has names, or if you have one on your screen or something, to look this stuff up. You'll always have access to a periodic table like this for quizzes and exams. You don't have to remember all the names and symbols. You probably will remember most of the common ones, but you'll have that as reference for all the other ones. So you look it up, and you've got sodium and chloride. The next step is to figure out what we just did. What are the most common ions of those two ions, or those 2 atoms? So sodium, we know its most common charge is what? +1, right? And chloride? -1. Yeah. And we did that really fast. You don't have to do it that fast. As you practice it, it'll get faster. If you don't know, you can do what we just did. You look for the valence electrons. You figure out how many it has to gain or lose. And then you write down that number there for positive or negative. So once we've got the 2 charges, we have to put them together in a ratio so that the overall compound is neutral. So there's as much positive charge in that compound as negative. With this one, it's pretty simple. There's just 1 plus from the sodium and 1 minus from the chlorine. So we just put them together like that, and we've got our compound NaCl. Once the compound is together and neutral, we don't write the charges up there anymore. We just write NaCl. All right, so let's look what happens when they don't equal like that. Sodium oxide. Same thing. We start the same way. We're going to write the Na for the sodium. And then oxide comes from oxygen. So that's going to be O. And then we find the charges. Sodium still plus. And what's the charge for oxygen? -2, right? So here's where it starts being a little bit different. We can't just put those two together and say that sodium oxide is NaO. Why not? They don't cancel out. The charges don't balance. We've got +1 from the sodium, but the oxygen is -2. So what do we do to make them equal? Yeah. Yep. So yeah, we need to double the amount of sodium here. And sometimes it's helpful actually to just draw it out like it's separate pieces like this. So you can see now there's 2 sodiums. That overall positive charge is +2. And those will get matched up with the 1 oxide. The overall charge is -2. So now we have +2 and -2. That's balanced. The way that we write that in a compound is we use the subscript number to show that in this compound there are 2 sodium ions for every 1 oxide ion. That's it. Think you can do that? All right, let's try a couple. I'm going to write some names like we just did, and see if you can write the compounds. When you think you've got one, talk to the people around you and see if you all got the same compound. So we'll try magnesium fluoride. Potassium nitride. If you have to look up some of these names to find the symbols, go ahead and do that. Just try not to look up the entire compound. See if you can build that on your own. And then finally, aluminum oxide. See if you can write formulas for those 3. Oh yeah, go ahead. In that container. It's kind of under this stuff. Yeah. Sorry, I'm the wrong button. All right, everybody got some formulas yet? Or still looking? Still working on it. Keep working on it. All right, let's take a look at these. I was looking around. Looks like a lot of good tries. If you didn't get the right formula when we talk about it, make sure you look at what you did put down and think about what you might have done wrong there. All right, so same procedure. We write down the symbols, magnesium and fluoride. Then we find the charges. Magnesium is a +2 and fluoride is a -1 because of their position in the table. Then we make the compound by adjusting the numbers. Since magnesium is 2+ and F is 1-, it's kind of the opposite of the sodium oxide we just did before. So our formula has to be MgF2 so that we have the same number of positive and negative in the formula. Yeah. All right, same thing with the next one. We've got K and we've got N. K gives us a +1. N we did earlier is a -3. So to get those to balance out, we need 3 of these. And in a formula that's going to look like K3N. You get that one? Head nods? Okay, good. Don't worry if you didn't. Got plenty of time to practice. And then the last one, this one is a little bit trickier. We put aluminum and oxygen. We know oxide is 2-. We've used that one before. Aluminum, we haven't done yet. What's the charge on that? 3+ or +3, yep. And so now we have to make a 3+ and a 2- even out by adjusting their ratios. Did anybody get a little stuck on this one at first? Then you had to kind of figure it out. So did you figure it out? What did you end up doing? Right. So what happens is, and you can kind of count it out if you don't know exactly what to do. If you try to add another oxygen, you now have 4- and 3+. So then you add another aluminum to compensate for that. And now you've got 6+ total and 4-. So then you got to add another oxygen. And if you keep doing this, you're eventually going to get to the point where they do balance out. In this particular one, it's when you have 2 aluminum and 3 oxygen. Having stranger imbalances than that doesn't happen much, but the 3 to 2 one is pretty common because there's quite a few 3+ ions. There's quite a few 2- ions. There's also 2+ ions with 3- anions. So when that happens, just know that you need to go 2 and 3, and then you just like switch the subscript for whatever the charge is. So if it's the one that's 3+, you get 2 of those. If it's the one that's 3, you get 2. You get 3 of those. Yeah. Yes.
Is that like a whole
That ties into this. We might get to it today, if not next week, but we will. Yep. All right. So you think you can do that? Build those compounds? All right. We're going to look at another class of ions now. These are the ones that we'll call variable charge metals. Up to this point, when we talked about charges, we talked about electrons and things. I keep saying, like, okay, just ignore the big clump in the middle. But the big clump in the middle is actually kind of important. There's a lot of stuff there that we need to use. So here's how we deal with the clump in the middle. Let's say we want to make the compound, iron chloride. So we can start the way we've been doing it. We look up iron on the periodic table. It's Fe, and chloride is Cl. And we know chloride is -1, but we don't know what the charge is on iron. And the reason we don't know is not just because we haven't learned it. It's because iron can take on different charges. And in fact, most of the metals in that whole big middle area of the periodic table can take multiple different charges depending on the compounds that they're making. So by just saying iron chloride, there actually is no way of knowing what the formula is supposed to be because we don't know what the charge on iron is. So when you see this, what happens is the charge actually has to be specified in the name. Otherwise, we don't know what it is. So there is no compound that's just iron chloride. The way that it would be written is iron with some number in parentheses, a Roman numeral number in parentheses. And that number in parentheses gives us the charge on the ion. So that tells us that in this particular compound, the iron is +3. Yes, metals are always plus. Now there's an older way of doing this. You may have heard something like ferric chloride or ferrous chloride. There's kind of older names, but that was confusing because you had to know what all those different names meant. Now we use this number in parentheses, makes things much easier because you can always tell what that charge is. Now this also introduces something that, for whatever reason, is always a big source of confusion in this class. Everybody wants that 3 to be a subscript. So everybody wants it to mean that you put Fe with a little 3 up underneath it to make your compound, and that's not right. It's not the subscript, it's the charge. So however you have to keep that straight, you want to make a little star, you want to circle it, whatever. That number in parentheses is the charge, not the subscript number for iron. It tells you what the charge is. You still have to balance the formula just like with any other kind of ion. So we have to say, all right, we've got an iron that's 3+, we've got a chloride that's -1. So if we make a compound, that means we need 2 more of these, right? So we've got 3- and 3+ overall. And that compound looks like this. See how that works? Okay, so try this one. copper 1 oxide. And if you get this one, that one, try this one. All right, so this first one, we got copper, we've got oxygen. If you don't know the symbol for copper, just look it up on the periodic table, it's Cu. And then we put in the charges, plus and minus 2. And that means that to make the compound, we need 2 of the coppers. So our compound is going to be Cu2O. We need 2 of the plus 1 coppers for the oxide. I don't know why, but again, just keep in mind that this is something that is probably not going to stick in your head very well, because whenever we do quizzes and exams on this stuff, and I ask a question like copper 1 oxide, everybody wants it to be CuO. Like copper 1 oxide means you just have 1 copper atom. That's not what it is. It's the charge. So we'll do whatever you can to remember that that number in parentheses is the charge. And then the second one, copper 2 oxide, we have now 2 plus and 2 minus. So those are those neutralize each other, 2 plus 2 minus. We don't have to change any numbers, and we just get CuO. In the next chapter, we'll also look at some naming next week, and it's really common for people to call this one copper 2 oxide because there's a little 2 there, but this is actually copper 1 oxide because that 1 is the charge. This is copper 2 oxide because, again, the 2 is the charge. All right. You okay with that? All right. So that's all the new stuff for now. We'll get into those other types of ions, polyatomic ions, and more on Tuesday. Let's take a look at Blackboard and at the lab for Tuesday, since we won't see each other before that. So the next lab is dealing with some of the stuff that we've been talking about, looking at ionic compounds and trying to put those ions together. It occurs to me, I don't know why there's highlights here, but probably from our editing, that the pre-lab questions, yes, okay, good. I was worried the pre-lab questions were going to ask stuff that we didn't do yet. But they aren't. They are not. So I think we're good. So this pre-lab is a little bit different from the previous one. The previous pre-lab was all about like just doing some general conversion skills to practice a little bit. This is more like a reading comprehension of the lab itself. Pre-lab. So this lab is checking to see, or this pre-lab is checking to see if you actually read the lab and you know what you're about to do. So please do it. You can, as with before, you can choose if you'd rather do it on paper and turn it in from a scanned paper, or if you'd rather just write it in your notebook, just write the answers in your notebook. You don't have to repeat questions. This lab is set up similarly to this week's lab, so you have the instructions, and then you have some data blanks for stuff, and it's again your choice if you want to write the stuff in the tables here, or if you want to organize it in your own way in your notebook. Okay, I know there's a couple people who have to finish up labs from Tuesday still too.
Is lab 2, are we able to turn that into Blackboard?
I doubt it.
No.
I don't think it's there yet. Yeah. So that'll be due on Tuesday. I'll probably set that up. So keep an eye out on the Connect system for the practice quiz popping up probably tomorrow morning. And so you can work through that at some point just to see what it's going to be like. And then we'll have that first quiz on Tuesday. All right. Otherwise, have a great long weekend. Don't forget there's no school on Monday. Those of you who are sticking around to finish up lab stuff, we can do that now.